Jenny, occasionally those gray boxes appear on the screen. Are they on yours as well?
Yes.
They're not a major, I mean, I'm sure we could walk our way around it if they crop up, but I just thought I'd draw to your attention, that's all.
Yep, that last box was me starting the recording, so. Well, let's go ahead and get started. I want to welcome everyone to our webinar today. This is hosted by the ASQ Statistics Division. Couple things just for housekeeping. We're going to have questions at the end, but feel free to type them into the chat or the QA whenever they come up so you don't forget, but we won't be answering them till towards the end of the talk. Then we'll go in and answer all the questions that we can. If you have trouble, we do have somebody monitoring the chat, so they'll try to help you with issues that you have during the talk, if any. After the talk, I will be sending out an email to everyone who attended with your RSUs or your credit for attending the webinar. I'll also have links for where the recording is posted on our YouTube channel and to links to our ASQ website where you can find slides and things like that if you want resources like that to look at again. So let me know if you have any questions on that. And I want to introduce our speaker. You'll be able to read along with me here, but we have a great speaker. He's done talks for us before. Lally Marwah comes to us from IBM and Nortel Networks, where he led quality systems and statistical applications. And then he also was at SSHA and TSSA in the public sector. As a chief statistician at IBM, he led deployment of statistical methods for improvement and control, which included things like SPC, designed experiments, sampling, and reliability, all the things you find in a Six Sigma program. He led the development and ISO 9001 registration of the global quality system at Nortel Networks, formulated quality strategy at SSHA as director, corporate quality, and served on the board of directors at TSSA. He's also taught applied statistics at the University of Toronto and other places, and conducted on-site statistics workshops at various companies and industry forums. He also represents Canada in the governing body of ISO 9001 and has chaired the development of ISO standards on statistical techniques and on customer satisfaction. He serves on several boards, such as the University of Waterloo, and he's also quite active in the ASQ divisions. I know he has several certifications with ASQ. So with that, I'd like to turn it over to Lally, and I'm sure we're going to have a great talk here. So go ahead, Lally.
Okay, thank you, Jenny. If you could, let's move to the next slide, which has our agenda for the day. And I want to spend a few minutes just basically talking to the agenda. We begin with this intro on the rationale for experimentation and specifically on two-level designs. Okay? And then move into various categories of two-level designs I'll begin with the standard order designs. We'll have some case studies from George Box and others. And I'll also touch on Taguchi designs, because that's a question that came up at the last presentation that I made. And there is still a sort of a lingering interest in the subject. So I thought I'd put those designs in the larger context of two-level designs. Before we finish, in fact, I'll also get into Plackett-Berman designs, which are another family of two-level designs, and which in turn are actually based on a totally different kind of a source for statistics. These are the Hadamard matrices developed in France towards the turn of the 19th century, early 20th century. And they resulted in the Plackett-Berman designs that we use today. And we'll end up with an open session and a bit of a review. So let's, with that, I'd like to move on to the next slide. Okay, so let's begin with the rationale for design experiments. Okay, all processes, it doesn't matter what process you're looking at, whether it's in a technical environment or administrative environment, marketing, and so on, they all are governed by multiple factors. The outcome is governed by multiple factors. And the factors can be quantitative, like temperature, speed, time, like something that you can measure, or they can be qualitative, just say type of material, A versus B, whether there's something there or not there. The outcome of a process then is really determined by the effect of each factor. That's called the main effect. It also is governed by the interaction between factors. And when you get into, we almost always have several interactions at work. And these interactions are actually key. Okay, we'll talk more about that later on. And we're also influenced by variation, random variation that we'll call noise. Okay. Now, before we leave the subject of interactions, let me explain that only two-factor interactions are considered in these experiments. And that's because the assumption is that higher order interactions, meaning interactions involving 3 and more factors, they are either don't exist or they are virtually negligible. And so we typically in statistics we disregard them. So we go moving on to the next slide. Okay, so now we look at that as a backdrop, look at the questions we face in process of improvement and problem solving. Okay. The goal in all cases is basically very similar. Okay, you're trying to identify the significant factors and the particular settings for those factors in order to achieve some desired outcome. And this, as a general statement, holds true for, again, any process. Okay? So the methodology we're going to be using is we use designed experiments to determine the main effect of a factor. And by the main effect, we're referring to an effect that is independent of all other factors. And we're also looking at the interactions that may exist between the factors. I want to emphasize a comment here on interactions. In most cases, interactions are unknown before we actually begin the experiment. And this has been my experience that even in very so-called mature processes that we've been running with, say, a couple of years, the interactions are often not recognized until we run these experiments. Okay? These interactions are important not only because they're part of the eventual statistical model, so they allow a more accurate model, but they actually provide insight into the cause of process behavior. And this information is key to a robust solution. Okay? And this becomes increasingly important when you get into complex processes. So to repeat, that's what we're trying to do now. So we begin with the experiment procedure. So we identify, as a first step, we identify the main product and process factors that may have a bearing on a characteristic of interest. That could be anything. Could be maybe measuring yield, maybe measuring defects, or whatever the outcome you're interested in. We have to first identify the factors that potentially have a bearing. Keep in mind that at this point, we don't really know. okay, which is why we're doing an experiment in the first place. So we need to, this is a very important part of the process, of the experimental process, because if you don't identify the key factors and the group of factors, the possible factors that you put forward, your results may not be conclusive. Okay. Having got the product and process factors, you then determine the settings, okay, to investigate the effect of each factor at the two various levels. For instance, the two levels could be labeled high or low, plus or minus, 1 or 0. These are the conventions that are typically used in textbooks, and any one of them will serve. Okay? And then we carry out the experiment using a design which is defined by a mathematical matrix. So let's look at an example. Next slide. Okay. So here's a typical kind of a layout, okay, of a two-level, what they call a two-level experiment design. You see on the right-hand side, you see a matrix. And we see three factors, A, B, C, that are labeled at top of certain columns. And for instance, the process factors in this case are investigated at two levels. An example could be, say, temperature at, say, 20 degrees minus versus 30 degrees plus. Okay. The design itself is defined by a mathematical matrix. And I won't go into the basis for the matrix, but this is what I'm calling a standard order matrix, and it's one conventionally used in most American textbooks, and American and British. If you're using a Hadamard matrix, it looks something different. The other feature to notice about this design is that all factors are tested simultaneously, and unlike what we taught at first in engineering school, was that if you want to determine the effect of each factor, then we basically keep everything else constant and move your one factor up and down. Well, in this case, we're doing it simultaneously, so which is contrary to what we've been told in school. Okay, and these factorial designs have a very high level of efficiency. So let's go into a further example. Next slide. Okay. So let's take, and this is really just to get us familiar with the working language of factorial experiments. Okay, so these examples are hypothetical, but they're intended to really illustrate how the factorial design serves as a basis for an experiment. Okay, in this case, you have four factors, A, B, C, D. Okay, and they're assigned in certain standard order. Okay, each row in that matrix, and I've labeled, you can see 8 rows. Each row defines an experiment run, or you can call it a trial. Okay? So trial number 1, for instance, if we read across and ignore the columns that don't have any factors assigned to them, then trial 1, for trial 1 has A at the minus level, B at the minus level, C minus, and D minus. The second trial has a different combination. A plus, B minus, C minus, D plus, okay, and so on, all the way down to 8 trials. With each experiment, as you run the trial, you measure, you record the response, okay, which in other words, the outcome of that particular run. Okay? And I'm calling it here X1, X2, X3, and so on. And these responses now are a basis for analysis. And they can be of any characteristic of interest. And the responses can be qualitative or quantitative. For instance, you can either have, say, let's say yield. You say that run had 5% yield or 10% yield or whatever the figure is. Okay? Or they can be purely qualitative. You look at it, let's say if you, as I've seen in a case study involving food, you rate the quality of the food product, let's call it a cookie. You call it, yeah, good, pretty, better still, best, and so on. It's entirely optional. Okay? You can use quantitative or qualitative responses. The other thing that I've not mentioned on this page is quite an important point. You can have several characteristics of interest that you can monitor for each run. So effectively, when you run an experiment, you are effectively running multiple experiments for different attributes. You could be measuring the outcome in terms of taste. You could be measuring the outcome in terms of cost. You could be in terms of speed, whatever, okay, whatever is of interest to you. So let's go on to the next slide. When you analyze the responses, and I've not gone to any specific details, but each of those columns in that matrix will when calculated will tell you what's contained, the effect of that particular column. Okay, so in this case, the first column A will measure the effect of A. The next column measures the effect of B. The column after that has two effects in it. It's got the AB interaction and the CD interaction, and so on, as you can see across. This is referred to as the alias structure. Okay, in other words, in this case, the main effects are all clear, but your interactions are confounded. But confounded means they mix up with each other. So this leads to quite an important dimension in design experiments, and it's central to the subject. Okay, so let's go to the next slide. Okay, the alias structure. We talk about experiment design resolution. This describes the clarity of the information that you get from an experiment. So in a full factorial, which is in the previous example would have been just ABC, you have a clear view of all main effects and all interactions, including high order interactions. If you have only a clear estimate of main effects and two-factor interactions, that's called a resolution 5 design. In a resolution 4 design, you get a clear estimate of main effects, but the two-factor interactions are confounded, in other words, mixed up with each other. And in a resolution 3 design, your main effects are confounded with two-factor interactions. So in other words, in the ideal case, of course, is a full factorial, but these tend to be very large experiments and very expensive and not necessarily the best value for money. Resolution 5, that's great if you can get it. I mean, again, it'll be a large experiment. Resolution 4, as you enter more and more factors into the same matrix, you start degrading the resolution. So with the resolution 4 design, you have a clear estimate of main effects, but the two-factor interactions are confounded. And in a resolution 3, which is the lowest grade, is where main effects are confounded with two-factor interactions. Okay. Now, ideally, of course, you'd like to start at the top, but in practice, okay, the experience is that a resolution 4 design will serve for all practical purposes. So if you can just go, Jenny, go back one slide. If you could just go back to the previous slide. Yes. So in this design here, for instance, this is a resolution 4 design where your main effects A, B, C are clear and D are clear, but your interactions, and those are all the possible two-factor interactions, they are mixed up with each other. Now, that's not a bad, too difficult a situation to deal with, because if A and B is mixed up with C and D, usually, if you know what the individual factors actually are, from technical considerations alone, you can determine that, look, AB is impossible, so it's probably CD, and so on. There are other rules that help you in determining which one of the two might be the significant one. Okay, so let's go on to back to the previous slide, next slide. So you've seen an example of a resolution 4 design, and these, for all practical purposes, are good enough to serve. In fact, most people like myself haven't had the luxury of running a full factorial, because they involve much larger designs, or even a resolution 5, because in practical terms, again, you need a lot of resources to run high level resolutions. So let's stay with the resolution 4 design for the moment and move to the next slide. Okay. So here's an important point about experiment design. Okay. A well-designed experiment can be readily analyzed using any number of analytical tools. If you're familiar with ANOVA, analysis of means, graphical methods, and so on, there's a whole raft of tools that we can use. But confounded effects in a poorly designed experiment can't be unraveled without a lot of further experimentation. So the emphasis in design experiments should be on sound experiment design. If you design it right, the analysis can be cut. You can cut the results several different ways to extract the information. But if the experiment design is wrong, or poor rather, then it's a lot more difficult task. So the focus of this presentation is entirely on sound experimental design. So let's move into a family. Okay, we're looking into now the families of experiment designs, and we're going to be talking about the standard order designs, and these are designs for they come in kind of blocks. Okay, 8 trial, 16, 32, and they can be, you can go on to 2 to the power of k. K can be any number. Okay, so but in practical terms, frankly, large number of trials, while they're theoretically possible, in practice and almost never get completed. Okay, what will seem like a very efficient alternative are the plaque and Burma designs, but they have certain limitations, and we'll talk about them when we get to them. And again, the objective and all of these designs is to extract the maximum information at minimum cost. And so in other words, the focus is on getting information on the main effect and the interactions, if any. And here's another point. The factors that are not significant in a context are also equally important, because this is very valuable information. I can cite examples where we choosing to see if the 2 different types of materials could be used. And if it turns out that the materials the material had no effect on the outcome, then it gives you the option of choosing the cheaper material, and so on. So we often ignore the fact that no matter what the outcome is, each information that we get from an experiment is in practical terms very useful. So let's go to the next slide. Okay, I'm going to talk to now the designs. So this is what first on a set of designs is the 8 trial design. In 8 trial, if you have only 3 factors, you're getting a full factorial. Once you add a 4th factor in the same design, the design resolution drops to resolution 4. If you go add more factors, 5, 6, or 7, you have increasingly sort of kind of alias designs. They're all resolution 3 designs. And the next is the 16 trial design. Like I said, it's 2 to the k. So the next matrix, the next order of matrix is 16 trial. With 4 factors, you have a full factorial. With 5 factors, it's a resolution 5. Anywhere from 6 to 8 factors, a 16 trial design will still give you a resolution 4. And from 9 to 16 factors, it becomes a resolution 3. So these 2, by the way, are probably the most widely used design matrices in the industry, and with good reason. Okay, but to complete our discussion on these designs, go to the next. This is a 32 trial design, and as you can see, with 5 factors, it's a full factorial, and very rarely would you run a full factorial for 5 trials, for 5 factors only, I beg your pardon, because that's overkill, the amount of resource that you're having to spend. With 6 factors, you still have a resolution 5. But from 7 to 10 factors, you can get a resolution 4 design, and the same with 11 to 16 factors. And you can go all the way up to 31 factors, but from 17 on, you're getting a resolution 3 design. Now, in theory, these designs, as I mentioned earlier, can extend to any value of k. Okay? But very large experiments can be impractical unless you're looking at modeling exercises on a computer. In that case, the sky's the limit. Okay? So, but if this is not a computer simulation, then in practice, I would say, and this is simply quoting my personal experience, 16 trials would suffice most of the situations. Okay, because when you brainstorm the process to identify significant factors that may have a bearing on an outcome, usually it's very rarely beyond that number. Okay, and my reservation about using the 32 trial experiments is that, in my experience, most times when they run them, people retire before they finish them. So, but just to give you the three main matrix designs for 8, 16, 32, and of course, in theory, they can go on to any number beyond that, like 2 to the k. It can take you up to a very large number. Okay. So let's go to the next slide. Okay. So when you're designing an experiment, typically all experiment design is a compromise between the number of factors to be investigated and the number of trials that you can afford. In other words, the circumstances allow. Okay. So when you essentially, it's not so much designing an experiment as picking an experiment. Either you identify all the factors that plausibly affect the outcome, outcome of interest, and then you select the highest resolution design that you can afford. In other words, within available resources. So I think at this point, we can go to the next slide. We can go on to look at some case studies involving factorial experiments. Okay. I'm going to spend some time basically going over these case studies because they illustrate a lot of the points that I've made earlier on experiment design. In this case study comes from George Box, okay, and is a part of his text that I've given below. Okay. And the objective in this case which is an injection molding process, and really doesn't matter what the process is, the principle applies to any. The intent here was to identify factors that influence something called shrinkage. Okay? The brainstorming identified 8 factors, and they will label them A, B, C, D, all the way up to H. Okay? And those factors were entered into a factorial design in that order. The placement of the factors in those matrices is important because they give you the optimal alias structure. Okay? So in this case, they entered those 8 factors into a 16 trial design, and the findings were interesting. Okay, the 2 significant main effects ended up as being C and F. Okay, which is C is in column 3 if you look up vertically, and F is in column 13. Oh, sorry, C is in column 4. Okay, and they also found a significant effect in column number 12. Okay, when they did the analysis. Column 12 contains the following interactions. It has CD, BE, AF, and GH. So one of those, okay, possibly all, but most likely only one of those is significant, and that it's real, it's an active one. And there's a very simple maxim in designed experiments that if you have an active interaction, it'll most likely involve one or more of the main significant effects. In this case, the 2 main effects were C and F. Therefore, the inclination was that it is going to be either AF or CD. And the technical opinion on the process supported the CD as a likely candidate, and this was verified in this particular case by a follow-up experiment. Okay, so the outcome of this experiment was, with the 16 trial design, was that they were able to identify which of the 8 factors identified was truly significant in terms of the outcome. The factors were C and F, and they also identified that the interaction that was most likely was actually C and D. In this case, not simply likely, but in fact was verified. So this is a kind of a synopsis of an experiment. The details are given in Box's book, but we've captured all the key points we want to make of this as an illustration of experiment design. Let's look at another case study. The next case study, if you can move to the next slide, is of an SMT process. This comes from my own experiment run on IBM, and which was presented at George Box's case study symposium at Wisconsin some years ago. Okay. In this case, the goal was to eliminate a certain type of defect. Okay, and the defect had caused the production line to shut down because the problem was discovered at a customer's. It had the effect of basically causing severe problems in the logic card and the connections. And essentially, we had to resolve this before we could start the process again. The brainstorming by the engineers, and this is again an important part of the process, the brainstorming involved all of the people that were involved in the process, namely the engineers, the manager, the operators, and the inspectors. I mean, so it is a combination of both people who had first-hand experience working on the shop floor and who are currently involved in the process, and the designers of the engineering designers of the process. And they identified 8 possible factors. Okay? Coincidentally, it just happens to be the same number of factors identified, okay, as Box's experiment. Okay, that's just pure coincidence. Okay? We ran a 16-trial design, and we found the significant effects were C, D, and column 12, which was CD. Okay. The active interaction in column 12 we concluded was CD, and that was determined purely by on technical grounds alone, because the other interactions were, the engineers believed, technically impossible. Okay? The CD interaction was very important because once we began to understand why the 2 factors were connected, immediately it pointed to the cause of the defects. And once we understood the cause of the defects, we were able to fix the process and immediately get to 0 defects. It was not slowly improving. It was a question of a quantum change, where you either have the right process or you have a wrong process. And in this case, we were able to get to 0 defects almost instantly. This is an important point about interactions. None of us, first of all, knew about it. Okay? And secondly, once we understood it, it pointed to a solution that went beyond the statistics. The stats analysis, I will remind you, is only a step towards the ultimate problem. It simply helps you identify significant factors and interactions, but the true answer ultimately is in terms of the physics and chemistry of the process. In other words, the causal factors. Okay? So this is a point that is quite important because it shifts the discussion from statistical to the technical arena. Okay? Now, let's go on to the next section, okay? Because that is pertinent to us. Okay, this is just a comment on what we've just seen. So it's a synopsis, really, what both experiments, case studies that we've illustrated. That the experiments yielded a very clear view of all main effects. There were no previously anticipated interactions, but the unknown active interactions were revealed, and these interactions provided insight into the process. So this is a segue into the next slide, okay? Because the next slide goes into discussing Taguchi ideas, because that's often comes up in these discussions. So let's we need to have a bit of a preamble here when we talk about Taguchi. Taguchi's work is interesting because, and we need to separate the significant elements or the philosophical elements from the practical applications. Okay, The first, let's look at the significant contributions by Taguchi. Taguchi proposes that any departure from some ideal value involves a loss to society, and the loss is quantified by a loss function. And that's a very interesting philosophical concept, because in engineering, we are otherwise used to a situation where everything within specs is good, everything outside of specs is bad, and therefore, it's a on-off situation. And Taguchi's analysis basically says, no, actually, there's a grading here. Okay, so we agree with Taguchi on that point. So Taguchi employs then factorial experiments to reduce loss and to make the product and process robust against variation. Total agreement there. Okay. The third point is, concern is not with Taguchi's ideas, but with his use of two-level designs and not his larger philosophy. So let's talk about his approach to the two-level designs. The next slide. Okay. So Taguchi's approach to design, and here we again want to keep reminding people that we're not questioning his philosophical ideas. We're questioning only the methodology used to get to those endpoints. The user, says Taguchi, must identify process factors, which is true. That's the same. But his approach also requires you to anticipate interactions. Big question marks, because in my experience and in the experience of many others, interactions are often unknown, which is often why you're doing the experiment. Okay? So these factors and interactions are entered into a two-level design matrix using a methodology developed by Taguchi called the linear graph. Okay, I won't go into those details. The limitation is that at the end of the day, it's not possible, okay, not always possible, maybe possible, it's not always possible to correctly anticipate interactions. And unknown interactions will typically confound your main effects. So the result is you end up with a lower resolution design with the same number of trials compared to a standard order design. And I want to give you an example here. The example is on the next page. Okay, this is from Taguchi's own case study. Okay, and by the way, I can point you to half a dozen case studies published by Taguchi and his team that illustrate the same situation. Okay? In this case, they're studying 8 factors, again 8 from A to H. Okay, and what I've done is I've taken Taguchi's design and simply mapped it into a standard order design for convenient comparison. Now, in Taguchi's design, he's got the result is that the alias structure is that only 2 effects, A and B, are clear, but 6 main effects are confounded with 25 possible interactions that he has not anticipated. Okay, what I've shown you below the red line, because when he talks about only identifying 3 interactions, the point is with 8 factors, you have another 25 possible interactions. What happened to those? They are all shown below the line, below the red line. And what you're seeing there is a very low resolution design. It's a resolution 3 where 6 out of the 8 factors are actually confounded with possible interactions. Now, the same experiment, I'm going to show you the same case study. If you took that case study and applied it into a standard order design, the next slide shows what you would get. Okay, if you could move to the next slide, same case study, and where you could basically see that in this particular, if you assign those factors A, B, C, D, E, F, G, H to the columns that you've identified on this page, you would get a result would be that all your main effects would be clear, not just 2, but all. Okay. Furthermore, the selected interactions would be confounded with other unknown interactions. But this design now is a resolution 4 design with the same number of trials. There's a fiction around, a prevailing kind of misimpression around that somehow Taguchi's designs are more practical or that they are cheaper to do. They're not. the math and the matrices are the same. And if you could go to the next slide, it sums up the two situations. Okay? As a general comment, Taguchi's approach to two-level experimental designs, okay, will typically result in much lower resolution design than standard order. And standard order designs typically yield better information with the same number of trials. Okay? So this is not to diminish Taguchi's work and his contributions to the philosophy of loss to society or the loss function. Those remain very interesting concepts. It's only the methodology that we basically sort of have reservations about, because in this case, he's drawing from the same pool. The math is still the same, okay? And it's a misapplication of the same tool, okay? So there are other issues regarding the analysis, but I've kept the discussion on analysis off the table for now, because the focus of this presentation is entirely on experiment design. But if it were, I just want to add that not only is the design wrong, but there are also some serious problems with the analysis, okay, in the use of the particular ratios that are used. Okay. So let's move to another family of designs. Okay, these are called the Plackett-Berman designs. Okay, they were developed by two English statisticians during the last war, during the World War II, that is, when there was a need to develop products new products at a very, very high rate, and they didn't have the luxury at the time to run large experiments. So they were dealing with large numbers of factors. Okay, so these Plackett-Berman designs are really interesting in that they allow you to investigate T-1 factors in T trials. That's, in other words, in 12 trials, you can investigate up to 11 factors. And all the way down to 36 trials, you can investigate up to 35 factors. Now, these are very economical, okay? But there's one problem. All your factor effects are unevenly confounded with fractions of all possible interactions. In other words, if an interaction exists, every column, every factor is basically aliased with fractions of different interactions. So you don't quite know, and it's not evenly distributed. So one column may be, let's say if A and B have an interaction, column A would be confounded with the other column would be confounded with, say, minus 1/3 AB plus 1/3 AB. Like it's a very complex aliasing structure. So what they're useful for are screening designs, where you take a large number of factors, pour them into a Plackett-Berman design, and simply identify the main or potentially significant factors, and then run a standard order design to refine that. And I should add that these designs actually come from a different source. Okay, if you can move to the next slide. Okay, here's an example, for instance, of a Plackett-Berman design. That's a Plackett-Berman design matrix. It's slightly different. If you compare this to any other, you'll find that the differences in the order of plus and minus signs. And I won't go into the logic of how these were developed, because that's theory. But I just want to add as a footnote, Taguchi's L12 array that he uses is actually a Plackett-Berman design, okay, with the rows and columns that are reordered. Okay. Now the Plackett-Berman designs actually, I need to basically move to the next slide. These designs are based on matrices derived from vectors, which are developed by a French mathematician, Jacques Hadamard, in France. And I think he died in the 1930s. No, and his work actually is very, very useful, because he developed his designs allow two types of designs. Okay, geometric designs. Those are equivalent to the standard order designs that we've already examined. You know, the R2, 8, 16, 32, and so on. those are actually what they call geometric designs. And Hadamard also developed non-geometric matrices, and these are the basis of Plackett-Berman designs. So Hadamard himself didn't actually do any experimentation, but his work formed the basis of the Plackett-Berman designs. Okay, and so really between the standard order designs that we've covered and the Plackett-Berman designs, you really have the entire spectrum, okay, of design experiments. The Hadamard matrices themselves were popularized by Bill Diamond, and a colleague of mine in IBM, and Bill sort of felt that somehow these designs had his matrices had a different properties, but in fact, when they examined carefully, they fall into the two categories that we've already considered. Okay, the geometric and the non-geometric. So that really covers. It's a bit of a crash course in the number of different types of different factorial designs that are out there. But in the standard order and Plackett-Berman, you have basically the mainstay of most of the designs that will serve industry or serve applications. I shouldn't say industry, serve applications everywhere, because I've been involved with some spectacular applications in marketing, where a marketing group was trying to identify the factors that would influence customer acceptance of a particular magazine in the US, which was trying to basically reach a particular demographic, and they considered various factors. The factors there were things like the color of the envelope, the type of print, and so on, the language in the material, endorsements by senators or not senators, and so on. So but at the end of the day, it's simply another process. And a design experiment there identified a huge finding, okay, which basically enabled that outfit to have a very significant effect on the success of that particular journal. Okay. So let's move on to the next page. So this is really just a high-level review of what we've covered so far. I wanted to basically, the idea was to lay out a whole range of designs that you could consider, and leave some room for a question and answer. But just to recap what we've looked at, we've looked at the wide range of two-level factorial designs. Okay, and these are mainly in the two categories of standard order, but I've called standard order rather, and Plackett-Berman. Okay. By the way, the standard order designs, I refer to them as standard order because they really are not original in that sense, and that the sources lie in existing material, existing maths. This is nothing new. The alias structures are developed by design generators that have been published a long time ago. Okay, so I prefer to just simply use the word standard order. Okay, all of these designs have high efficiency. They're maximum information with minimum resources. Okay, they are applicable to product, process, and service analysis and improvement. Okay, and they are in all phases, in the design, development, production, verification, and they're also applicable to all sectors. Okay, traditionally, experimentation has been either in the manufacturing side and development side in the hardware world, in science and engineering, in pharmaceuticals, but the roots of this work was in agriculture, and of course in the pharma now world of science and medicine, they touch almost every aspect of science and medicine. Okay? And so I haven't listed. I put together initially a list of applications that I've encountered from amongst my classes at U of T, but I figured that they come from a wide range of different disciplines. They're very useful as illustration, but really there's little point in examining each one of those. Okay? So I thought this way it will leave the floor open for more time for comments or questions that you may have. So I'll turn this over to you, to Jenny and to Gary, if you want to basically, sort of, if you have any questions, I'd be glad to accept them.
Thank you, Lally. Excellent presentation. There are some questions, so I'll go through and get some here for you. Let's see. So I'll do one here. What is your opinion of using Minitab for DOE, and what are the biggest potential pitfalls?
Okay, Minitab, by the way, for those who may not know, this is a software package, and it has all kinds of very neat features. Really, it's a matter of using anything that basically is convenient. I would suspect that the designs that Minitab has would correspond to standard order designs. I've not made any reference to software in this course or in my classes, in fact, because a simple Excel program will solve nearly everything. Okay, so once you understand the theory and the maths, it really, you can use virtually any software. And I've tended not to use any of the standard packages. I've tended to use just a small routine, and Excel would do it. Okay. The main value of software is actually in the graphics. They basically allow you to plot your results very clearly, very conveniently. And those later on, when you start doing more detailed analyses, they become useful because it's less of a pain to do a plot of residuals, a plot of graphic effects, and so on, with the software package than to do it manually.
Thank you. Another question. What is usually the next step after 2K factorial designs and experiments in terms of process optimization? What tools/theory should I research?
Well, okay, there's a range of more sophisticated statistical applications, and that I think get into a different sort of area of analysis. Okay, I think we all are familiar with CCDs and so on, and the idea is not here was my focus was really on the basic design to get to identify the main factors. Quoting personal experience, in practical terms, we rarely had the opportunity to, or the luxury to do more sophisticated analysis. Usually, you can get 95% of the information with the first experiment, and they usually has not been in production anyway. The patients to spend more resources going after the remaining 5%. Okay, so I know it's not a satisfactory answer, but I'm telling you there are other tools. They're well known. The textbooks written about it. George Box has written a wonderful book on it. But my focus has really been on getting people kickstarted on two-level designs.
And by CCD, you mean central composite designs, just to somebody doesn't know.
Yeah, thank you, Jenny.
Okay, another question. In terms of practical application of the findings from the experiment design, do you find it more typical to resolve all factors observed as actively interacting, or to attempt to control one of those factors to prevent an interaction you don't want?
Well, by definition, every factor in a process has significance and importance. But your purpose here in conducting the experiment and using the results is that you've identified the main factors. Okay, they're really what they call significant factors, statistically significant factors. And so I don't know if that answers the question, because yes, the other factors are important, but the focus is typically on the significant factors and on acting on the information that you gain from the interactions.
All right, so there's a few questions. I believe that this presentation has been recorded and will be placed on our statistics division YouTube site. And I believe there are also, I think the slides can be shared. There's a PDF, I think, available, and I'll leave that to Jenny to decide how those are distributed. And there was a question here. I was under the impression Taguchi was mainly used as screening experiments.
Well, I've not seen a lot of the work on Taguchi is aimed at not just screening experiments, but as in the same sense as we would use uh, the standard order designs. So regardless of whether you use it for screening or as an experiment to determine the significant effects, I can't see any advantage in using Taguchi's work because when there are better alternatives available.
Okay.
The concern one has is that it's often a remark of this nature is misread as dismissing Taguchi's work, whereas in fact his work on the idea of lossless society, loss function, I think is profound and has real value. Okay, so I don't. So here's the dichotomy is that I think all sort of engineers and statisticians who are familiar with his work do respect his contribution in terms of philosophy. It's a methodology that we basically have some reservations about.
All right, thank you. Another question, which design would you use if your response is a attributive characteristic? And do you do data transformation for attributive response?
Okay, if your response is an attribute, like percent or whatever, I understand there's some very sort of well-known routines and Box has codified them of transforming that. The idea of transformation is that you transform the response into a measure that is normally distributed. Okay, and so depending upon the kind of whether it's a Poisson distribution, whether binomial or whatever, there are responses, there are standard conventional responses around, and so the response that you would pick would be appropriate to the particular kind of data that you have. I think that I think I've got the question, but I just want to make sure that I haven't missed the point here.
Okay, thank you. If the factors you wish to test are a few and are known, can you employ more than 2 levels if your objective is optimization?
Well, okay, we come to the question of, and Taguchi and others have played with three level designs. Okay, the trouble with 3-level designs, and it's difficult to demonstrate this without a blackboard, but you assume that between the high and the low or whatever setting you've got, that you can extrapolate further. Okay, with whatever finding you have. The point is you don't know that. Okay, and so I think if you're going to go beyond that, then some of the tools that have been put forward, like CCD that we talked about earlier, would be probably more appropriate.
All right. So there was an individual that asked, can we invite you back for another presentation? He thought this was excellent, so that's good. And maybe Lally will entertain us next year in 2023. You never know.
Sure.
One other question, I think this will be the last one. What is the high number of resolution designs that can be obtained? Resolution 10 question mark?
Well, I think the full factorial would be that, I guess, because the full factorial will give you not only the main effects, but every possible interaction. So the utility of full factorial is often questionable. So the 3, 4, and 5 would be the rest. So I don't know that there is any such thing as a resolution 10, but if there were one, that would in effect be a full factorial. I realize that he's using the word resolution 10 as a figure of speech rather than real.
Yes. All right. So I'm going to thank you again, Lally, for this excellent presentation. Very informative and I believe practical for users. And Jennifer, I think there were questions about RUs, etc., and I'll leave that to you to just let the attendees know how things will work relative to slides and posting and RUs and that kind of thing. Thanks again, Lally.
Cool. Thank you.
Yes, thanks. Thanks, Lally. I mentioned it at the beginning, but you may have missed that. I will be sending out an email with all the credits, and I'll also provide the links to the slides and the YouTube channel for everyone then. So that should give you all you need. If you do have any other questions, feel free to respond to that email, and I'll give you whatever else you might need then.
Okay, thanks everyone.
Okay, thank you.
Thank you all.